Okay, so what we are going to do is we are going to continue with our variational calculation. What we did on Friday is we wrote down the BCS pairing Hamiltonian, which is this first line. It is a very simplified Hamiltonian. It contains only this term as the interaction term. We wrote down the BCS wave function. It is a variational wave function. It has many variational parameters. For each k, there are two variational parameters, uk and vk. And uk and vk satisfy this constraint, that modulus uk square plus vk square is 1. And what we want to do is we want to do this variational calculation where we want to find out what these variational parameters are by minimizing the ground state energy. So we have to minimize this because we are in the grand canonical ensemble at 0 temperature. Now, using this constraint that uk square plus vk square is 1, we can parameterize uk and vk as two angles, sine of an angle and cosine of an angle. So uk and vk can be written in this form. So now you have used for all k, you have used this constraint, and for each k now you have only one variable, which is theta k. So then we have to minimize this quantity as a function of this angle theta. So we do that, and what we find is this equation here. We find the value of theta k that minimizes h minus mu n. So once you find the value of theta k, you found the values of uk and vk, so you have the ground state of the superconductor. So this is the equation that we get when we try to minimize this quantity. Now in this equation, we define a new variable which we call theta of k, which we'll discuss the physical significance of this in a minute. It's defined as basically the numerator times a factor of -12. So what this equation, it just becomes this. So this delta of k now includes all dependence of this potential vkk prime. Now this equation here is an equation for tangent with a minus sign. You can find out what sine and cosine are. Because there is a minus sign, you can choose this minus sign either in the sine or in the cosine. We choose it in the cosine because we expect when k is very large, when this energy psi k is very large, we expect vk to be 0. Because vk square gives us the probability of pair of states k up and minus k down being occupied. For very large energies, we expect them to be not occupied, so mod vk square should be 0. So if this is 0, we get the right signs. If you use some other parameterization here, you may have to pick another sign. So this is where we stopped yesterday or Friday, and now we are going to continue with our calculation. Next, what we are going to do is we are going to again assume that the potential is only finite in a small energy range. So we are going to use what is called on-shell approximation. So we have vkk prime. This is some attractive potential independent of k and k prime only if both energies are within a small energy window of the Fermi energy. Now, if you look at this expression here, this is a function of k. The only dependence on k comes from this factor here, VKK prime. So if we make this approximation that VKK prime is just some constant attractive potential, there will be no K dependence on the right-hand side. That means within this approximation, this quantity delta should be a constant. So this approximation implies that delta K is delta, some constant inside shell, and is 0 outside. Any questions so far? So now this already is a big simplification, making this approximation. Let's put delta to be constant here. Now, what is this sine 2 theta k? This also involves delta. So let's write down what equation we have is delta k is equal to minus half sum over k prime VKK prime delta k prime Now in this equation, if we put delta k to be a constant, so within this approximation, this is the equation that we obtained by minimizing the Hamiltonian, and now within on-shell approximation, we know that delta should be a constant. If you put delta to be constant here and here, you'll see one factor of delta will just cancel out, and you'll be just left with this one. So the equation that you will have is 2 divided by V is sum over K 1 over square root delta square plus K square. Now again, this is we do this many times in condensed matter. Whenever we have sum over K, convert it to an integral over K, and then from this integral over K, convert it to an integral over energy by using the definition of density of states. So we have already done it a few times in this course, so I'm just going to write down the result. Again, I'm using G as function for the density of states. Now again, I'm going to assume that the energy scale h bar omega c, that is the energy scale where we have attractive interactions between electrons, is much smaller than the Fermi energy. And with this approximation, I would assume that the density of states does not vary much at the energy scale of h bar omega c. So I'm really interested in very small window of energy around Fermi energy. So very small window. So this h bar omega c is much smaller than Fermi energy. And with this constraint, I'm going to ignore any energy dependence that the density of state has in this energy window and take this outside the integral and just replace it by the value of density of state at the Fermi energy. So when we do all of this, what we will get is this integral. Now this integral can be done easily, and what we get is sine hyperbolic inverse Any questions? Any questions? So this approximation also we've seen multiple times. Now let's see what does this mean for delta. From here you can calculate what delta is. So delta is h bar omega c sine hyperbolic 1 over Vg epsilon f. And now again we are going to make another approximation, which is the weak coupling limit. Which is V times the density of state at the Fermi energy. This is much smaller than 1. And with this approximation, you would find out that delta is approximately 2 h bar omega c exponential minus 1 over V G E F. So now we have found the variational solution. We have found the value of delta. Once you know the value of delta, you can figure out what the value of, so in this approximation, delta is just constant. You can figure out what the values of thetas are. Once you know what thetas are, you can figure out what UK and VK are. Another thing we can see from here is in the weak coupling limit, if this quantity is small, that makes this whole factor very small. That means this energy scale delta is much smaller than energy scale h bar omega c. So we start with an assumption that there is a small window of energy over which we have attractive interactions between electrons, and then we use the variational ground state, and what we find is that a new energy scale emerges in the problem. This new energy scale delta is much smaller than the energy scale h bar omega c. So now we have 3 energy scales in the problem. Yes.
So sometimes I think we've said that the energies that we're talking about should be above the Fermi surface. So we go from like epsilon f to epsilon f plus h bar omega c. But here we seem to be integrating below the Fermi surface as well. Why do we sometimes do that and sometimes not?
So when you do the integral in k space, then you always would have wave vector k to be larger than kf. But whenever you are in energy space, you assume that you have some negative energy also. So the difference is whether you are in energy space or momentum space. And actually, this is a very important point that you make. The reason I'm doing that is later on, I will see that throughout this process, we will basically need holes in the problem to understand superconductivity. So this negative energy window will play an important role later on. Yes?
Seems like omega c is kind of an arbitrary parameter, so how is that determined physically?
So it is not arbitrary in the sense that it is the energy. So physically, it is the energy window where you have attractive interactions. So outside this energy window, you don't have attractive interactions. So at the moment, we haven't assumed anything. It's arbitrary in a sense. But what we are going to assume, the reason that we assume there are attractive interactions is because of phonons. So we should keep in mind that this h bar omega c is actually related to phonon energy scale. So you can think of, so I called it a new variable h bar omega c because its relation with the Debye frequency involves some other factors. But you can think of this omega c as really Debye frequency. So some energy scale of the order is Debye frequency. Any other questions? Yes.
What is the justification for delta k to be constant?
So in this equation, the left-hand side, I have delta as a function of k, and right-hand side, I have sum over k prime. The only place where you can have a k dependence comes from this vkk prime. And for the on-shell approximation, we are ignoring any dependence on k or k prime. So you can see that that means within this approximation, delta should be a constant. So now we can find out, now we know what delta is, we know what theta is. Let's see what uk and vk are. So we have these two equations, vk square minus uk square. This is equal to minus pi k over ek. So in a moment, ek is going to be square root delta k square plus psi k square. And we also have vk square plus uk square to be 1. So ek is square root delta square plus chi k square. So from this, I can calculate vk square to be half 1 minus chi k over ek. So this is really my solution. So for each k, I found out what uk and vk are. So now I have a description of the ground state of the superconductor. We can also make a plot of these uk squares and vk squares. So let's make a plot as a function of psi k. Let's say this is 0, and this is really minus infinity. what you'll find that this curve here, this is Vk square, this is Uk square, and now you can see that there are some energy scales that are very important for us. So this 0, when chi k is 0, that means you're really at the Fermi energy. So this is really at the Fermi energy. So far above the Fermi energy, the probability that you have a Cooper pair occupied is 0. That's given by Vk square. And what we have found is also probabilities for Uk square, and that is given by the inverse of this Vk square. So what I've done is just plotted these two functions here. Any questions? Next, what we are going to do is...
Yes, I have a question.
Yes.
What is lambda on the what does it represent on the
Delta?
delta, sorry.
Yeah. So what this delta represents is what we will plot the next quantity in a minute. We'll plot another quantity and we'll see. So it represents a gap that will open up at the Fermi energy. And in a minute, we'll plot another quantity that will tell us more about it. So for the moment, if you remember our calculation from Friday, you can check that if you calculate expectation value of Ck up dagger, Ck up in the ground state, this was equal to Vk square. Also, expectation value of Ck down dagger or minus K down, this was also Vk square. So from this, physically, we can think of Vk square as a function of K that is giving us the occupation probability of single electrons also. So we know mod Vk square is the occupation probability of a Cooper pair, which is K up, 2 electrons, 1 K up and another minus K down. Now, if in our ground state we only have electron pairs, then this probability is also related to the occupation probability of single electrons. So we did this calculation in detail on Friday. So this is just to motivate us that, so this motivates us that the single electron occupation probability is related to Vk square. So if we, on top of this, so this is a plot at 0 temperature. We have minimized H minus mu n. This is how Uk square and Vk square look like. If we plot the Fermi function at Tc, at a finite temperature, which is the critical temperature of the superconductor, if we plot experimentally, we figure out what Tc is, and we know the dispersion, we can make a plot of Fermi function at Tc as a function of energy. What we find is that this Fermi function is similar to Vk square. So 0 temperature Vk square is similar to Fermi function at Tc. This is an observation. From this observation, one can say that kBTc should be of same energy scale as this new energy scale delta, because in a Fermi function, you have this variation at the energy scale kBTc. So if you assume kBTc is of same order as delta, which we have calculated within the weak coupling limit as 2h bar omega c So now what we can say is the following. So the transition temperature of a superconductor is related to delta. And now this delta, we can see that it depends on omega c. What is omega c? We just discussed that this omega c is related to phonon frequency or the Debye frequency. It's an energy scale for the phonons. How does the dispersion relation of phonon look like? So it goes as square root of K over capital K over M, and then you have mod sine Ka by 2. So this is the dispersion relation of phonons. That means this energy scale omega c really goes as 1 over square root of capital M. That means Tc goes as 1 over square root of capital M. And this was one of the things that we knew experimentally, the isotope effect for the superconductors. So this theory can explain isotope effect measured by experiments. So now let's try to gain some insight into what this energy scale delta is. So from this, to match with experiments, we related this energy scale with kBTC. What we'll do next is we'll think of another quantity, which is expectation value. So all these expectation values are in the BCS ground state, not in true vacuum. So I'm going to make a calculation where I calculate expectation value of 2 annihilation operators. If I do this, what I will find is that this expectation value is same as UK star VK. So again, use the same tricks that we used on Friday to calculate the expectation value of 2 particle operators and 4 particle operators. We can compute this expectation value in the BCS ground state, and this is what we will find. Now, what is UK VK? This you can see from this equation here. That is simply given by half sine 2 theta k. So this is simply half delta k over Ek or we can, assuming that delta is constant, well, we can write the full form. And if you plot this quantity now, so plot this expectation value on the same plot, what you will find is that UK square, VK square, this will look something like this. So this is really UK VK. So expectation value of 2 annihilation operators really looks like this in the BCS ground state. It is something that is finite over this energy scale delta, and it vanishes outside this energy scale. So what does this tell us? This gives us a hint that if we are looking for an order parameter to describe a phase transition at the Fermi energy. So remember, in what is order parameter? It is defined as a quantity which is finite in one phase and is 0 in another phase. So when you go through a phase transition, if this phase transition is related to breaking a symmetry, then you can always find an order parameter that is finite in one phase and is zero in another phase. So if I'm looking for an order parameter, this might do the job because this is really only something that is finite at the Fermi energy and over this new length scale delta, and it vanishes at all other energy scales. But this again just a hint, as it is with mean field theory, or with phase transitions, it's not straightforward sometimes to think about what the order parameter really is. So here you can think of it as a hint, or you can try this guess. If it works, great. If it not, then we'll find some other order parameter. But the key thing to remember here is this is a quantity that is only finite over the energy scale delta. And it quickly vanishes. It's not something that is at the energy scale of attractive interaction of the phonons. Any questions? So now we have a description of the ground state of the superconductor. And we have already explained the isotope effect, but we still have to explain many other properties of the superconductor. We have to explain all the other features of superconductor, zero resistivity and Meissner effect and all other facts that we observed. To explain all of these quantities, what you need is also excited states. So far we did variational calculation that told us a lot about the ground state. It gave us the ground state of the superconductor, but we would also like to find out some information about the excited states. So we can describe a superconductor at finite temperature, for example. Now, this method is not useful to describe excitations in a superconductor. So what we are going to do is, again, we are going to do a mean field theory, and we'll use this as our mean field parameter. So goal again is to start with this BCS pairing Hamiltonian. It's a very complicated, it's very simple Hamiltonian as compared to the most general Hamiltonian, but it's still complicated because it has 4 operator terms. So the goal is to convert that 4 operator term into 2 operator terms and use the deviation operators that we discussed in mean field theory and derive a simplified mean field Hamiltonian. So I'm going to define delta K as So I'm going to define this as my mean field, this as the expectation value. And what I will try to do is I will try to replace, for example, those 2 annihilation operators on the last 2 operators in that 4 operator term. I'll replace those 2 operators by those 2 operators minus their expectation value, which really is given by this. So when you go through this whole calculation, introduce deviation operators, and derive the mean field Hamiltonian, which only has 2 operator terms, this would look like, it will have only single operator terms, but it will have terms that don't look like number operator. So when you try to simplify the 4 operator term to include only 2 operator terms, you can see that with this as the mean field parameter, if you define deviation operators with 2 annihilation operators, you will be left with a term that has 2 creation operators. Similarly, you will be left with a term that has 2 annihilation operators, and now you have delta K star here, which is expectation value of 2 creation operators. So this Hamiltonian, it is quadratic in the sense that it only includes 2 operators, but it does have operators in a very weird form. It now includes a term that has 2 creation operators and a term that has 2 annihilation operators. So what we would like to do next is to simplify this Hamiltonian or do a unitary transform or try to diagonalize this Hamiltonian. So this Hamiltonian, it does have some weird terms, but it is a single particle Hamiltonian now. And what we would like to do is find the eigenstates of this Hamiltonian. Yes?
That annihilation term, does it spin up on the second seed?
Oh, yeah. So I think I can write this as, yeah, let's write it down, minus K up. So always we'll have pair K up with minus K down and K down with minus K up. So this Hamiltonian can be diagonalized, and it can be diagonalized using a trick which is known as Bogoliubov-Valetin transformation. And what we would like to do is, first we will recast this Hamiltonian in a matrix form. So I can write down this Hamiltonian as sum over K So what I've done is just rewritten this line in a matrix notation. When I do this, you can see that what this will give us is a term minus psi k times annihilation operator C minus K down, C minus K down dagger. So when you anti-commute these two, you will get this factor. So you can show that these two are exactly same. I'm just writing this in matrix notation. Next, these last two terms don't have any operators. So these are really constant terms. The operator is just identity. So they don't have any creation or annihilation operators. So we'll ignore the effect of the last two terms, and we're really focused at diagonalizing this Hamiltonian. So what we have is the mean field Hamiltonian for the BCS theory. This is sum over K, a vector AK dagger, HK, AK, plus some constant terms. Constant means they don't have any creation and annihilation operators. So this AK is really a column vector with CK up and C minus K down dagger. Any questions? So what I'm going to do next is to perform a unitary transformation such that I have diagonalize my Hamiltonian. So I'm going to write this H BCS mean field as sum over K AK dagger. I'm going to insert this identity here as UK dagger, UK dagger. So you can see that if we try to diagonalize this Hamiltonian, we have to apply a unitary transformation to this vector AK, which is a vector that consists of annihilation operator and creation operator. So here already we can see that when we diagonalize this Hamiltonian, the new eigenstates will be a superposition of annihilation operator and creation operator. So I can define BK as UK dagger AK, and in this with this BK, what you will find is that the BCS Hamiltonian, it will be sum over K BK dagger, and now you will have something diagonal here, BK. So after this unitary transformation, you will have diagonalized the Hamiltonian, and the new basis states are now UK dagger multiplied by AK. And you can say that in general, these new basis states would be superposition of annihilation and creation operator. So by imposing this constraint, so any 2x2 unitary matrix, I can write in the following way. So this is a unitary matrix. You can check determinant of this is 1. So this is a general way of writing a 2x2 unitary transformation. And we have already imposed, we know UK and VKs, we know mod UK square plus mod VK square is 1. So what we are going to do is now impose the constraint that this unitary transformation diagonalizes this Hamiltonian. That means you know the original Hamiltonian. It's given by this matrix. Impose the constraint that U dagger, this Hamiltonian HK, U is a diagonal matrix. By imposing this constraint, you can find out what these U's and V's are, and you can also find out what the eigenvalues are. So what we will find is mod UK square So we find the same solutions that we found using the variational calculation for UK and VK. So I chose these parameters in a way that I will get this answer. So this is just a general way. We don't know what U's and V's are. General way of writing down a unitary transformation. Impose the constraint that the matrix is diagonal. You'll get these values for UK square and VK square, absolute value square. And this, when we did the variational calculation, we assumed UKs and we parameterized them as real, and we had the same answer for same solution for UK square and VK square. So we can already see that this mean field theory is in agreement with our variational calculation. Also, when we find the eigenvalues, what we find is you can write down the eigenvalues as EK and minus EK, where EK is again square root So now you have UK and VK. You can write down. So what we are going to do next is write down what this equation really means. What this equation means is BK, which we are defining as some new operators, and I'm going to call it gamma K up, gamma minus K down dagger. Let's use simple brackets. This is same as UK minus VK, VK star, UK star, and now you have the electronic annihilation and the creation operator. So what that really means is gamma K up is UK CK up minus VK C minus K down dagger. And gamma minus K down dagger is VK star So these UK and VKs, they're also called BCS coherence factors, and the entire superconducting, the theory of superconductivity is now encoded in these UKs and VKs. So we have new operators, gamma K up and gamma minus K down. And in terms of these new operators, the Hamiltonian is diagonal. So we have the eigenstates, but these new operators are really superposition of electronic creation and annihilation operators, and they have these coherence factors, UK and VK, in them. So you have a simple theory of superconductivity in terms of very complicated operators. So you have the eigenstates, but the operators really look like this. So you can also invert this equation and write down these electronic creation and annihilation operators in terms of these new operators, gammas. Any, yes?
What does it mean to create a superposition of an electron and a hole?
So an excitation, it is a single particle excitation, but what it does is it creates two so it's a superposition. Each term has only one fermionic operator, but what it does is in one term you are annihilating an electron, which you can see as creating a hole, and in the other term you're creating an electron.
Seems a little bit counterintuitive.
Sorry?
It's a bit counterintuitive.
Yes, so what we can do next is try to gain intuition on what these operators really are. But it is counterintuitive because superconductivity as a phase is something very different from the normal metallic phase where we have only electrons. So it is counterintuitive, I completely agree. And it was a difficult problem. It took a long time to solve it for this reason. But we can understand a bit about what these new operators are by drawing the dispersion relation. So let's do it next. What you can see from here is that so within on-shell approximation, we found out that this delta K was constant. Even if it's not a constant, let's say it's some function of K and that has no zeros. In that case, you can see that the excitations, so these are the diagonal values, plus Ek and minus Ek. They must have a gap. What that means is if you look at positive energy eigenvalues, all these positive energy eigenvalues at least have a value of delta K. So delta K is like a gap. All excitations must be above delta K. Another way to see it is, so what we have is, let's make a plot of, so what are the eigenvalues? So the eigenvalues of this new diagonal Hamiltonian, these are really plus minus Ek. And what is this energy? This is the single electron dispersion minus the chemical potential, which at zero temperature is the Fermi energy. So what I'm going to do is make a plot. So this, you can assume that this is h bar square k square over 2m minus mu. So I'm going to make an attempt to draw these two eigenvalues. And I know that this eigenvalue, so what is the new Hamiltonian? The new HBCS mean field is actually sum over K. I have Ek and I have gamma K up, dagger gamma K up minus Ek gamma minus K down, gamma minus K down dagger. So after my unitary transformation, this is the Hamiltonian that we have. Plus, there are terms that don't have gamma operators at all. So you can think of this term as a single particle creation operator and this term. So we are going to call this term as creating particles or quasi-particles, and this term will be seen as creating quasi-holes. So this gamma k, this gamma k up dagger is creating a quasi-particle, which is same. If you look at gamma k up dagger, you have to take dagger of this equation, gamma k up dagger, which is uk star ck up dagger. So what this gamma k up dagger does is it creates ck up dagger with uk star, and it annihilates c minus k down with minus vk star. So this creation operator for a quasi-particle for real electrons, it creates and also annihilates something. This we are calling gamma minus k down. This operator we are calling as an operator that creates a quasi-hole. What this really means is take dagger of this equation, you create something and annihilate something. So what we would like to do is to gain some intuition about these quasi-particles and quasi-holes. So what we are going to do is, first we are going to start with the simple parabola, which is, this denotes, so these are energies, and we are plotting it as a function of k. So this is h bar square k square over 2m. Then I'm going to plot the chemical potential mu. So imagine that at t equal to 0, you start with parabola and you're creating the metallic state before the superconducting phase transition. So fill up all electrons till the Fermi energy. So this is, I'm just plotting this. This is the line that denotes mu. So this is really kf. So all states, so this is k, energy as a function of k. I'm plotting this parabolic dispersion, and all states below kf are occupied, all states above kf are empty. So this just denotes original electrons. Next, I'm going to plot within the original theory. I'm going to double the original theory and include holes in it. So if you just have electrons, you cannot describe these new quasi-particles just in terms of electrons. So you need to double the original degrees of freedom. What I mean by that is, on top of this electronic branch, I'm going to draw a branch that is that is a reflection of this curve about chemical potential. So I'm going to draw a curve that looks like this. And this is electrons. And this is holes. This branch represents holes. Next, so this is electrons here. This is holes also here. Next, what I'm going to do is I'm going to make a plot of Ek and minus Ek. So what Ek and minus Ek look like is the following. So you have, this is Ek. So this orange curve, this represents plus Ek, and this one represents minus Ek. So this plus Ek corresponds to creating a quasi-particle which corresponds to gamma k dagger, gamma k up dagger, gamma k up term, and this bottom branch, this represents create a quasi-hole. So this is really the gamma minus k down, gamma minus k down dagger term. So what we have done here is we also assume that this gap here is 2 times delta K. So one way to understand these new eigenstates of the superconductor is to start with electrons and then holes, then also include holes in your theory, and then include some hybridization between electrons and holes, and then you can think of these two new eigenstates as plus Ek and minus Ek. And now this plus Ek, the quasi-particle branch, includes, if you look at this energy, each of these energy values includes both electrons and holes, which is what we wanted from this theory. So what you have is, again, this is Kf. So all states below are empty, are full, sorry. So you can think of all these electronic states to be occupied and all those hole states to be occupied. But above Fermi energy, all electronic states, which are here, were empty, and now the hole states were also empty. So you can also think the usual analogy between electrons and holes. So above Kf, it costs some energy positive E above the chemical potential to create an electron, and some negative energy above chemical potential to create a hole. And so this is a way to think of these new operators, quasi-particle and quasi-hole operators.
Sorry.
Yes?
I don't understand, because usually holes are just an equivalent way of treating electrons, but we never mix the two things because usually it doesn't make sense. So I don't really know how we can do this here.
So one way to think of this is just a physical answer. You can also show it mathematically, but physically you can think of what really is the BCS ground state. So it consists of a lot of terms, and these are a term with no Cooper pair, with 1 Cooper pair, with 2 Cooper pairs, 3 Cooper pairs, and infinite Cooper pairs. This is really the ground state of the superconductor. So number of electrons, so the BCS Hamiltonian also does not commute with the number operator. So in this state, already you can see that the number of particles is not conserved, right? So that means you can always add or remove particles at will. So one way to think of a hole is to think of a missing electron and think of the following process. So you start with only single electrons, and then think of superconductor that consists of pair of electrons. Now, because in the ground state, number of particles is not conserved, superconductor is allowed to do a scattering process where it absorbs the one electron that you had, takes another electron from a reservoir, makes a Cooper pair, and what is now left is a missing electron, which is a hole.
I still don't understand the thing you do now, but okay, never mind.
So you can think of as so the only reason. So what's bothering you is why superconductor couples electrons or holes, or
Just the picture, actually, because I don't know. Just because I'm used to the fact that we can mix these two terms, I mean, that we can say this, we can treat this as holes or electrons separately, but not mixing these two and just.
so as long as you are not dealing with a superconductor, that picture is correct. So you can think of superconductor as a phase of matter that actually couples electrons and holes.
Okay.
And it is allowed to do that mathematically. You can understand this because the wave function for the superconductor only conserves parity, which means only conserves number of particles modulo 2. So if you start with even, because it has these two creation operators, two annihilation operators, that means if you have one electron, this is actually also same as one hole with a coupling. And this coupling is described by a process where you take one electron, take another electron, make a Cooper pair. And this process, you've actually created a hole. And this process provides the coupling between the two. Yes?
So is only the bottom band gonna be full in the ground state?
So in the ground state, that's a very good question. So in terms of these new operators, the ground state has no quasi-particles at all. So in this picture, the ground state is denoted by this here. No quasi-particles at all. So actually, that's a good question. Let's discuss. Also, there will be problems in the homework where you would show this explicitly. So what ground state would look like is, so you can show that gamma. So in the homework, you would show this. So typically, we think of vacuum as annihilation operator acting on vacuum gives us 0. Now, in terms of these new quasi-particles, gamma and gamma daggers, which are represented by those two curves, what we have is all of these annihilation operators with k up minus acting on ground state give us 0. So this ground state is really the new vacuum. You can think of the ground state as the new vacuum, and on top of this vacuum, you have those excitations. So the vacuum for those excitations is really the BCS ground state, which is where you have one Cooper pair, two Cooper pair, three Cooper pair, up to infinite Cooper pairs. That is the new vacuum for this theory. And the energy for this vacuum, just think of at the Fermi energy. So the BCS state, in terms of these operators, is defined as a state that has no quasi-particle or quasi-hole excitations. So sometimes these gamma dagger, these operators are called Bogoliubov bonds, just a name to honor the scientist Bogoliubov. So you can define the ground state as absence of any Bogoliubov bonds, or just simply its absence of any quasi-particle or quasi-hole excitations. Yes?
So sorry, are you saying here that the quasi-hole has negative energy? Like, wouldn't that make it energetically favorable to have lots of quasi-holes instead of none of the ground state?
So at finite temperature, so in terms of, so here you can see that you have, you can use, we will do some, if you use, you can put that minus sign by, if you use the anti-commutation, let me just write down the anti-commutation relations. You can also show, so you have gammas in terms of C operators. So from that, you can show the following, that gamma K up and gamma minus K down. This commutator is 0 and gamma K up, gamma K up dagger. This is really so you can also think of that negative as use this anti-commutator, add some constant energy, and then you will create these particles. So essentially, what you're doing is you are never really annihilating something. Every time you annihilate something, there is a coherence factor UK and VK. It also corresponds to creating something. So from the analysis that, we can lower down energy by annihilating something, one would expect that we can annihilate all particles. But what you can do is annihilate all Broglie bonds, all of these new operators. And that is indeed true. The ground state is a state with no excitations at all. But always think of creating a particle, quasi-particle, or a quasi-hole as doing something, as creating an electron and also a hole, or annihilating an electron. Any other questions? Yes.
How do you know that the BCS analysis is always valid for all cases and not only? So we only, when we did the analysis, we did the approximation for the potential. We only consider a small window around the Fermi energy. Here we kind of extend.
Yeah. So, well, this picture also, it's really true close to Fermi energy. Far from the Fermi energy, as you said, like the scale for attractive interaction is assumed to be much smaller. This new scale delta is, so let me say it this way, that is not to scale. So the Fermi energy and delta there look like on the same scale, but far away from Fermi energy, we don't expect this to be true. And another answer is, well, if it is not a good approximation, later on we are going to calculate like some numbers, and if it's not a good approximation, you would see that it does not agree very well. But indeed, what we find that this is a very good description, even far away, even if you relax the approximation, even in the energy window outside, between delta and h bar omega c. So, any other questions? Yes.
To create a quasi-particle, you have to provide energy to the system to bridge the gap. But superconductors are only superconducting at cold, like below
low temperatures.
Right. So which would seem like if you were to cool it down, then become superconducting, it seems like you're taking energy out of the system.
So before superconducting transition, you really have normal state where you have Pauli's exclusion principle, where you have all electrons, single electrons, and each K state is only occupied by one single electron, and you have Fermi energy and so on. Or at finite temperature, you have chemical potential and you have Fermi-Dirac statistics that you can create some excitations at finite temperature by providing the single electrons energy of kBt. Now, when you cool down the system, Fermi surface is no longer there. So the system is, what we are describing here is really something that is not at all equivalent to the picture of free electron gas that we discussed earlier. But now the question of creating a particle or excitation. So now this new state, it really is at t equal to 0, the new state is described by only Cooper pairs in the system. And now your question of how to think of creating excitations in this ground state. Now in this ground state, when you create an excitation, say you are at finite temperature, then you will have to provide some energy, say kBt. And what this kBt will do is this energy will create both quasi-particles and quasi-holes at the same time.
So in a sense, it's destroying the...
Yep. And again, the only reason all this can happen is because the ground state really does not have a conserved particle number. You are allowed to destroy another particle at will. Any other questions? So next we are going to do precisely that. We are going to look at expectation value of these new operators, or define a number operator that consists of gamma operators and calculate the expectation value at finite temperature. So now we really want to explain why TC is like, we want to now make some quantitative predictions from this theory and see how they do as compared with the experiments. So one of the most important things about mean field theory is to calculate these expectation values using the self-consistency criteria. So that is what we are going to do next. So we define delta K as minus sum over K prime, VKK prime, C minus K prime down, C K prime up. So you can show that in terms of the new, you can write these C operators in terms of gamma operators. And this now will involve the BCS coherence factors. So what we are going to do here is we are calculating these expectation values at finite temperature. So don't put this annihilation acting on the state is equal to 0. Yes?
So the expectation value is not on BCS but on a thermal.
So you can think of the expectation value of the operator here really as this 1 over the partition function trace e to the power minus beta h times this operator. So h is the mean field Hamiltonian. So this is just for the self-consistency criteria. So from this we already know that these gamma operators are really fermionic operators. So these excitations, the new excitations, are also fermionic excitations. So we have ground state that consists of Cooper pairs, which are bosons, have 0 spin, but the excitations are fermionic. So now what I'm going to do next is use, I think I'm missing a dagger here, use anti-commutation relations of gamma operators and write this down. So what I'm going to do is write it down as follows. So what I did is just I wrote this as 1 minus. I used the anti-commutation relation. So minus of this and minus of this. Now what this is it's an expectation value over a number operator of a fermionic particle, fermionic quasi-particle. And the same thing here. So you can always replace this at finite temperature at equilibrium by the Fermi-Dirac statistics. So what we will do next is we are going to write this as minus sum over K prime one minus 2 times this eta f e k prime, where this eta f is Fermi-Dirac distribution function. Any questions so far? So I have expectation value of gamma dagger gamma, which is the expectation value. What have I really done? I really wanted to calculate this expectation value of 2 annihilation operators. I wrote it down in terms of new quasi-particle and quasi-hole operators. What I got was an expectation value of quasi-particle operators, which was the last term, gamma dagger gamma, and an expectation value for quasi-hole operators. I converted from quasi-hole to, again, particle representation using the anti-commutation relation. And then finally, I am replacing expectation value of a number operator by Fermi-Dirac statistics, because I can do that only if this is number operator for a fermionic particle. And I've proven that these are fermionic particles by these anti-commutation relations. So if you try to do this integral in general, so now it's a sum over k. It involves vkk prime. So all of the structure of the problem is in there. Again, what we are going to do is to simplify and do the on-shell approximation. So what we are going to do next is, again, the on-shell approximation. And within on-shell approximation, vkk prime is just going to be minus v if both energies k and k prime are within h bar omega c or is 0 otherwise. Within this approximation, you will find that this delta, again, you will see that within this approximation, delta should really be a constant. This is same as what we did earlier. The only dependence of k comes from vkk prime on delta, so it must be a constant. And this can be written, so convert the sum over k into an integral over k, and then convert it to an integral over energy, and then use the definition of density of states So start with the sum over k, convert it to integral over k, use definition of density of states, convert it to an integral over energy. Again, use the fact that the dependence of density of state on this density of state does not vary on the energy scale of h bar omega c. Replace density of state function by its value at the Fermi energy, take it outside the integral. Now delta is constant, so you can cancel this factor of delta with this here. And this is the equation you have. So go through all of these steps and show that finally you can arrive at an equation which is known as the BCS gap equation. Now this equation use some tricks of the exponential function. You can write this as tangent hyperbolic beta by 2 So this is known as the gap equation. What that really means is this equation will give you the solution for delta, which we know is the gap in the spectrum from the definition of capital E case over there. So next we have to do is solve this equation. Also keep in mind that this equation does depend on temperature. So this equation does have all the information that we want. This equation can be used to calculate the value of Tc, the critical temperature, and that is what we will do tomorrow. We are going to start with this equation, and we are going to solve this equation at 0 temperature, and then at Tc, at the transition temperature, and then we'll make a prediction, and what we will find is that this prediction is going to be in excellent agreement with experimental numbers. Any questions? So let's do this tomorrow. Thanks.